So now we're going to look at a couple of uses of the Pythagorean identity. The first one we're going to do is just to say, well, if this is true, can we fill in the blank on exercise 4? I do want to point out when we have this identity, notice that this is the same variable. So we're not saying any sine value plus any cosine squared or cosine value at each of those squared and added equals 1. It has to be the same angle. Okay, so when I say here, for example, the sine squared of pi over 4 plus the cosine squared of something equals 1, this angle will be pi over 4. Now, later you'll learn there's other angles, and even if we look at the unit circle, there's other spots where the cosine is the same as the cosine of pi over 4, but we usually just keep that angle the same. It does not work for any angle. It should match the angle we have. So here, if I have sine squared of an angle plus cosine squared of 100 equals 1, this would also have to be 100 degrees. So it works for degrees or radians, just the angle has to be the same. So here, if I see sine squared of pi plus cosine squared of pi, since the angle is the same, those two would have to add up to 1. Just to verify this, I'm going to take this example. So we know the sine of pi over 4 is radical 2 over 2, sine of 45. Now remember that squared is written in a weird spot. It means this value squared. The cosine of pi over 4 is also radical 2 over 2. So if I do that, does that equal 1? So if I square these, and you could just type this on your calculator to verify it, but I'm just going to do a little math here. This would end up being radical 2 squared would be 2. 2 squared would be 4. And then this fraction would be the same. So we get 2 over 4. Is 2 over 4 plus 2 over 4 1? Yes, that's true. So 1/2 plus 1/2 is 1. And that's a super simple one because that we know at 45, the sine and the cosine have the same value. But any pair, okay, so if I did 30 and I did sine of 30 is 1/2. 1/2 squared plus radical 3 over 2 squared would also equal 1. And any angle I pick, even stuff that's not on the unit circle, that's true for. So here's one way we'll use it. It says Rebecca is working with angle A. She thinks the sine of A is 1/3 and the cosine of A is 2/3. So we're going to use the Pythagorean identity to determine if Rebecca is correct. Explain your answer. So if she's correct, unless she's messed them both up to the same other angle, this value squared, so 1/3 squared, plus 2/3 squared should equal 1, right? If they go with the same angle, we should be able to square them both, and they should equal 1. So looking at my first fraction, this gives me 1/9. This one gives me 4/9. That is not equal to 1, that's equal to 5/9. So no, her values do not work. In the Pythagorean identity. They work in sine A plus cosine A equals 1, but not when we square, which is what the identity says should be true. So now it says Rebecca checks her work and she realizes that her value of sine A is correct, but her value of cosine A is incorrect. So what she's going to do is she's going to draw a triangle. And I should, oh, it does say quadrant 1 good. So otherwise we wouldn't really know the signs of this. So if this is A, the sine A is 1/3. If I'm going to solve for this side so I can find the adjacent side, we are going to get that side squared is equal to 8. And when we take the square root, 8 is 4 times 2, so this is 2 radical 2. So now we know that the cosine of A is really 2 radical 2 over 3. Now just to check, we can use our Pythagorean identity. So we can check now. So is 1/3 squared, that was her correct sine value, plus 2 radical 2 over 3 squared equal to 1. So we have 1/9. If I square and distribute here, we can distribute exponents over multiplication. I get 4 times 2. So that is 8. Distribute down here, 9ths equals 1, and that checks. And interestingly, if I look at these values, right, here's my 1, here was the 8, and there's the 9. So you also kind of get a feeling for the fact that you're just kind of checking your Pythagorean theorem, but with the fractions, because now we've made the ratios. So it's similar, and that's why we call it the Pythagorean identity. So to summarize here, how is the unit circle helpful? 1, we just started to see it allows us to work with trigonometric functions without using a triangle. Because the hypotenuse is always 1. All we need is a point on the unit circle, xy. So if we know a point, we learned today that we can find all 6 of the trig functions. This allows us to extend the trigonometric functions to any angle, not just those that fit in a right triangle. And we'll see this even more in the next lesson. So when I'm here, we have a point on the unit circle, let's say here at like, I don't know, 200 degrees. There's some point, and the x of that point is the cosine of 200, and the y is the sine of 200. Now, there's no way I fit a 200-degree angle in a triangle, right? It just wouldn't fit. But we can find, and there are valid values for the cosine and the sine of that angle. We know the x value of the point on the unit circle is the same as the cosine of the angle that's intersected at that point. And the y value is the sine of the angle. Write the word of in here. Also, and as I said, we'll talk more about this tomorrow, and we did talk about it in the unit circle lesson. Those points on the unit circle, we can't draw a triangle for those points, but it does let us find the trigonometric values of those quadrantal angles. Where we cannot draw a triangle. The unit circle also gives us the Pythagorean identity. Showing a relationship between the sine and cosine of any angle, which we just learned today. And it is also the basis for creating the graphs of sine and cosine, and also graphs of tangent and secant and cosecant and cotangent.